Welcome back, Apologia, Physical Science, Week 20, Day 3 continued. This is the study guide for Module 9, questions 8 through 15. All right, question number 8. You are watching the lightning from a thunderstorm. You suddenly see a flash of lightning, and 2.3 seconds later, you hear the thunder. How far away from you did the lightning strike? The temperature at the time is 13 degrees Celsius. Okay. So to determine the distance, we will use the time difference between the lightning flash and the sound, that 2.3 seconds. We will assume that the light from the lightning reaches our eyes essentially at the same instant as the lightning was formed. Thus, the time it takes for the sound to travel to you will determine the distance. First, we need to know the speed of the sound. All right, so step 1, write down the list of knowns and unknowns. We have the temperature at 13 degrees Celsius. We have the time at 2.3 seconds, and we're trying to figure out the speed in meters per second. Step 2, write out the equation. The speed equals 331.5 times or plus 0.6 times the temperature in meters per second. Step 3 and 4, substitute the numbers into the equation and solve. So we end up with the speed equaling 339.3 meters per second. Step 5, now we should use equation 6.1 solved for distance. Distance equals speed times time. Step 6 and 7, substitute the numbers into the equation and solve. So we figure out our distance is 780.39 meters. So that is how far away from you the lightning struck. Question number 9. Sound waves are traveling through the air and suddenly run into a wall. As the sound waves travel through the wall, do they travel faster, slower, or at the same speed as when they were traveling in air? Sound travels faster in solids than it does in gases or liquids. Thus, the sound travels faster in the wall. All right, so number 10 goes with number 9. In the situation described above in number 9, what happens to the amplitude of the wave? Is the amplitude of the wave smaller, larger, or the same as the amplitude before the wave hit the wall? Okay. Remember, when a wave strikes an obstacle, part of the wave is reflected. So part of it's automatically reflected, and part of it is transmitted through the obstacle. Thus, only a portion of that wave actually starts traveling through the wall. This means that the amplitude of the wave will be smaller because only part of the wave is present in the wall. All right, a jet aircraft is traveling at Mach 2.5 through air at 1 degree Celsius. What is the jet's speed in meters per second? All right, so to determine the speed of the jet, we first must determine the speed of sound. After all, Mach 2.5 just means actually 2.5 times the speed of sound. So we need to find the speed of sound and then multiply it by 2.5. Okay, step 1, always write down the list of knowns and unknowns. We have the temperature at 1 degree Celsius. We're trying to find the speed in meters per second. Step 2, write out the equation. The speed equals 331.5 plus the quantity 0.6 times time, meters per second. Step 3 and 4, substitute numbers into the equation and solve. We're able to get the speed as 332.1 meters per second. So once again, that is the speed of sound at 1 degree Celsius. So now, since the jet is traveling at Mach 2.5, we have to multiply the speed of sound times 2.5. So 332.1 meters per second times 2.5 gives you 830.25 meters per second. Number 12. A jet travels through air at 464.1 meters per second. If the air has a temperature of 0 degrees Celsius, at what Mach number is the jet flying? All right, so this is pretty much the same as the problem number 11. So to determine the Mach number, we know how quickly sound travels in that air. Then we just divide the speed of the jet by the speed of sound. This will tell us how many times faster than sound the jet is traveling, which is what the Mach number is. All right, so step 1. Write down the list of knowns and unknowns. We have the temperature at 0 degrees Celsius. We have the speed of sound that we're trying to find. And then we have the speed of the jet, 464.1 in meters per second. Step 2, write out the equation. So we're trying to find the speed of sound. 331.5 plus the quantity 0.6 times the temperature. Step 3 and 4, substitute the numbers into the equation and solve. Well, anything 0.6 times 0 gives us 0. So the speed is just that, 331.5 meters per second. So that right there is the speed of sound. All right, so step 5, divide the speed of the jet by the speed of sound. So 464.1 meters per second divided by 331.5 meters per second is 1.4. So that means that the jet is traveling at Mach 1.4, or 1.4 times the speed of sound at 0 degrees Celsius. Number 13. Why do jets travel at speeds of Mach 1 or higher only in sparsely populated regions? When a jet travels at Mach 1 or higher, it creates a shock wave of air that causes a very loud boom. This boom can damage people's ears and buildings. Thus, sonic booms must be avoided when people or buildings are nearby. It just reminds me of the flyby scene at Top Gun. If you're old enough to watch that, you'll see what happens. Number 14, a guitar player is plucking on a string. I typed something wrong there. A guitar player is plucking on a string. If he takes his finger and pinches the string to the neck of the guitar so as to shorten the length of the string, will the pitch of the sound emitted increase, decrease, or stay the same? All right. Since the string becomes shorter, the wavelength will be smaller, and this will result in a higher frequency. And just keep remembering that I keep saying wavelength and frequency are inversely proportional to each other. So if the wavelength will be smaller, you know the frequency will be higher, and thus the pitch will also increase. And lastly, 15, you hear two musical notes. They both have the same pitch, but the first is louder than the second. If you compare the sound waves of each sound, what aspects of the wave, the wavelength, the frequency, the speed, the amplitude, would be the same? What aspects would be different? The wavelength, the frequency, and the speed will all be the same. After all, the pitch is determined by the frequency, which in turn determines the wavelength. The speed depends only on the temperature. The amplitudes of the waves will be different, however, because amplitude determines loudness. Alrighty, I put these slides together quickly, but hopefully they're helpful.